I have spent years dissecting this problem, consulting with professionals across 3 continents, and writing back-to-back comparisons between factory-mapped machines and properly tuned ones. What I found should make every rider who spent $15,000, $20,000, or $30,000 on a modern motorcycle furious. What I'm about to reveal is not a feature. This is not safety engineering. This is a systematic deception built into every modern motorcycle sold today, and it is getting worse with every model year. Chapter 1. The Invisible Wall. The hidden performance gap is the single most misunderstood phenomenon in modern motorcycling. A rider purchases a machine rated at 120 horsepower, rides it for 6 months, and develops a nagging, persistent sense that something is fundamentally wrong. The bike pulls strongly above 6,000 revolutions per minute in 4th, 5th, and 6th gear. But in 1st, 2nd, and 3rd gear, at the throttle positions most used on real roads and in real traffic conditions, the response feels blunted, disconnected, like the engine is operating behind a pane of frosted glass. They take it to the dealership. The technician connects a diagnostic tool, reads 0 fault codes, and tells them the motorcycle is performing to specification. That sentence is the most important sentence in this entire video because it is completely true and completely dishonest simultaneously. The motorcycle is performing to specification. The specification includes deliberate powers, suppression across the lower gear range, and the partial throttle positions that represent 90% of all real-world riding inputs. The rider paid for 120 horsepower and received a machine electronically capped to deliver a fraction of that in the conditions they actually ride in. Here's the data that the brochure omits. 3rd gear, 40% throttle opening, 4,000 revolutions per minute. This is the throttle position a rider holds while filtering through urban traffic, while accelerating from a junction, while overtaking on a rural road. On a factory-mapped modern leader-class machine, the engine management system is deliberately throttling the throttle valve opening to somewhere between 50 and 65% of what the mechanical components are capable of delivering. The engine hardware contains 120 horsepower. The software is releasing approximately 70 to 80 horsepower at that input, in that gear, at that speed. The remaining 40 to 50 horsepower is sitting locked behind a wall of firmware, available on a dyno, unavailable on a road. A phantom specification that every manufacturer advertises and no untuned motorcycle can fully deliver on a public road in normal conditions. The invisible wall is real, it is documented, and it is only the beginning of the problem. That blunted throttle response is not a mechanical flaw, it is a software decision. And to understand exactly how that decision is implemented, you need to understand what happened to the throttle cable. Chapter 2. Mechanical connection versus digital request. There was a physical wire. It ran from the right handlebar grip through a cable housing directly to a throttle valve on the intake tract of the engine. You twisted the grip. The cable pulled. The valve opened. The engine received more air. Fuel followed. Power was produced. The relationship between your hand and the engine was direct, immediate, and mechanical. Unfiltered, uninterrupted, honest. That wire is gone on every significant modern motorcycle sold today. What replaced it is a ride-by-wire system, and understanding its architecture is the key to understanding every problem this video covers. In a ride-by-wire system, the throttle grip contains a position sensor. When you twist it, the sensor measures the angle of rotation and converts that measurement into an electrical signal. That signal travels to the engine control unit, a computer. The ECU reads the signal, consults a 3-dimensional map stored in its memory, cross-references the current gear, vehicle speed, engine temperature, battery voltage, lean angle sensor reading, and barometric pressure, then decides how much to actually open the throttle valve. A separate electric motor, called a throttle actuator, physically moves the valve based on the ECU's decision. You made a request, the computer evaluated it, the computer responded independently, without consulting you further. You did not command the engine. You submitted an input to a system that has already decided in advance through programming completed in a laboratory by engineers you will never meet, exactly how much of your request to honor in every possible combination of conditions. This architecture enables every advanced safety system on a modern motorcycle: traction control, launch control, cornering ABS, wheelie control. These systems are genuinely valuable and genuinely save lives. The problem is not that ride-by-wire exists. The problem is what manufacturers do with the additional authority it gives them over engine output. The throttle valve position map inside a factory ECU is not engineered to maximize performance or optimize the riding experience. It is engineered to pass regulatory tests. Specifically, it is engineered to minimize noise output during drive-by noise testing, minimize emissions output during emissions certification, and produce the smoothest possible response during the specific test cycles regulators use for homologation. The rider's experience on an actual road is a secondary consideration in that engineering process. The mechanical cable gave you direct authority. The digital system gave the manufacturer final authority. And the organization deciding how that authority is used is not your riding preferences. It is the European Commission. The emission standards that reshape this architecture have a name, and what they have done to engine tuning is something every rider needs to understand before signing another finance agreement. Chapter 3. The Euro 5 Death Grip. Euro 5 emission standards became mandatory for new motorcycle type approvals in January of 2021. Euro 6 regulations are already being phased in, with full implementation advancing through this decade. Every major motorcycle manufacturer selling in the European Union, the United Kingdom, and the dozens of markets that mirror European standards must certify every new model against these requirements. This includes almost every significant motorcycle market on Earth. The emissions targets these standards impose are aggressive. Carbon monoxide limits dropped significantly compared to Euro 3. Hydrocarbon and nitrogen oxide limits tightened to levels that fundamentally constrain how an engine can be tuned. Meeting them requires running the engine on an air-to-fuel mixture that is dramatically leaner than the ratio that produces optimal power, optimal smoothness, and optimal engine longevity. A lean mixture means less fuel relative to the available air. When an engine runs lean, combustion temperatures rise. The exhaust valves, the piston crowns, and the cylinder walls are exposed to thermal loads that are genuinely higher than the engine was designed to sustain during normal operation. Manufacturers compensate through improved materials and tighter cooling tolerances. They cannot fully eliminate the thermal consequence of a lean calibration. The result, measurable on a wideband oxygen sensor and felt by every rider who has sat in summer traffic on a Euro 5 machine, is catastrophic heat output from the engine. Riders report heat from the headers, the radiator fans, and the exhaust system at levels that were not present on pre-Euro 5 machines of equivalent displacement. This is not an individual fault. It is a direct consequence of the lean mixture required to reduce carbon monoxide and hydrocarbon emissions to regulatory levels. The lean calibration produces 3 additional problems beyond heat. First, it causes lean surge, a rhythmic, deeply unpleasant oscillation in throttle response at constant partial throttle positions, particularly between 3,000 and 4,000 revolutions per minute. The engine pulses. The rider's body rocks slightly forward and backward at a frequency that is deeply unpleasant on long motorway journeys. Second, it contributes to stalling during low-speed maneuvers because the lean mixture provides insufficient fuel to maintain combustion stability at idle when the engine is thermally loaded. And third, it creates a jerky, abrupt throttle response from rest because the ECU overcompensates for the lean condition during the first fraction of throttle opening, producing a snatch that makes the low-speed riding needlessly difficult. These are not manufacturing defects. These are regulatory consequences. The manufacturer did not want this. The regulator required it. The rider pays for it. And the paying does not stop at the purchase price, because once you understand what lean calibration does to the throttle response, you will recognize the specific electronic symptoms it creates. Chapter 4. Mapping the dead zones. Connect a laptop to a modern motorcycle's diagnostic port. Open a tuning application that can read the factory ECU map. Navigate to the throttle position table, the 3-dimensional map that governs how much the throttle valve actually opens in response to rider input. Look at the values for first gear, then second, then third. What you find in the data is what professional tuners call the dead zones, and they are everywhere. In first gear, the factory throttle position map on most modern leader class and mid-displacement machines caps the throttle valve opening at between 55 and 70% of maximum, regardless of how far the rider opens the grip. The mechanical capability to open the valve fully exists. The software refuses to allow it. The reason is not rider safety, despite what the press releases say. The reason is that first gear full throttle inputs represent the conditions under which drive-by noise testing is conducted. The throttle restriction reduces engine noise output at the specific measurement point regulators use. Passing the noise test requires capping the throttle response in first gear. In second gear, the restriction persists. The valve sealing lifts slightly, typically to between 70 and 80%. The underlying reason shifts from noise compliance to emissions compliance. Second gear acceleration is the load condition under which certain emissions test cycles operate. Restricting the throttle opening reduces fuel delivery, leans the mixture, and lowers hydrocarbon output during the test. In third gear, the restriction begins to lift but does not disappear. Partial throttle positions in third gear are where lean surge is most pronounced, and where the ECU applies the most aggressive fuel subtraction to meet carbon monoxide targets. The rider requests 50% throttle. The computer opens the valve to 42%. It delivers a fuel quantity calibrated specifically for the emissions test cycle, not for the public road. The rider experiences a flat, lifeless, disconnected response that communicates nothing truthful about what the engine is actually capable of delivering. Above fourth gear, on most machines, the restrictions ease substantially. This is why modern sport bikes feel alive on an open road in fifth and sixth, and dead in urban conditions. The regulatory tests that impose the restrictions are not conducted at motorway speeds in high gears. The manufacturer was not required to restrict those conditions, so they did not. The dead zones are not random. They are precisely placed to satisfy the specific test conditions of the certification process. They bear almost no relationship to the conditions in which real riders actually ride real motorcycles, and resolving them requires intervention that the manufacturer has made financially and procedurally expensive. How expensive exactly? That answer will make your jaw drop. Chapter 5. The Hidden Tuning Tax. A modern middleweight motorcycle, 600 to 800 cubic centimeters, retails in the United Kingdom for between 8,000 and 12,000 pounds. In the United States, equivalent machines are priced between $8,500 and $14,000. In Australia, between $12,000 and $18,000 Australian dollars. These are significant financial commitments. They represent months or years of savings for most buyers. The purchase price does not buy you the motorcycle the engineers designed. It buys you the motorcycle the regulators permitted. To access the machine the engineers actually built, you need an ECU flash. A professional ECU reflash from a reputable tuner with a dyno-verified custom map costs between $800 and $1,500 in the United States, between $600 and £1,200 in the United Kingdom. The price varies by machine complexity, tuner reputation, and whether the work includes a base flash only or a full custom dyno pull map. This is the hidden tuning tax. Every buyer of a modern Euro 5 machine should factor it into the purchase price, because without it, they are riding a deliberately compromised machine. The manufacturer knew the factory map was a regulatory concession, not an engineering optimization. The dealer knows. The aftermarket tuning industry built its entire modern revenue model on this knowledge. The buyer is the last person in the transaction to find out. The tuning industry has responded to this reality with increasing sophistication. Companies like Woolwich Racing, Bajaj, Dynajet, and numerous independent tuning specialists have developed proprietary flash tools for almost every modern motorcycle platform. These tools bypass the manufacturer's read and write protections, allow the tuner to access the base calibration tables, and replace them with maps that restore the air-to-fuel ratio to stoichiometric or slightly rich values across the operating range, remove the artificial throttle position ceilings in first, second, and third gear, and optimize the ignition timing advance curve for the actual fuel quality available in the rider's market. The cost is real, the benefit is also real, but there is a legal and financial consequence that every buyer must weigh before booking the appointment. Warranty voiding. Flashing the ECU on a motorcycle under manufacturer warranty voids the powertrain warranty in almost every jurisdiction. The manufacturer's terms and conditions explicitly state that modification of engine management software constitutes a warranty exclusion event. If the engine subsequently fails, for any reason, the manufacturer is legally entitled to deny the warranty claim on the basis that the calibration was altered. This creates a genuine dilemma for buyers of new machines still within their warranty period. The smart money has an answer to that dilemma, but it requires understanding exactly what a proper tune actually does to the machine before deciding when to do it. Chapter 6. Restoring the engineering intent. A proper ECU reflash is not a modification, it is a restoration. To understand the distinction, you need to know what the factory ECU map actually is versus what it was designed to be before the regulatory concessions were applied. Every modern motorcycle engine is designed by engineers who are attempting to maximize a set of performance and reliability objectives. They want peak power. They want broad torque. They want smooth, predictable throttle response across the entire operating range. They want low operating temperatures. They want long valve and piston service intervals. The base engine map, the calibration that reflects those engineering objectives, exists inside every manufacturer's development database. It was tested, it was refined, it was validated. Then the regulatory team arrived. The base map was revised to meet Euro 5. Fuel was subtracted. Throttle ceilings were imposed. Ignition timing was retarded in specific load zones to reduce hydrocarbon output. The map that leaves the factory on every production machine is the base map, minus the regulatory subtractions. A proper ECU reflash restores the air-to-fuel ratio across the full operating range to values between 12.5 to 1 and 13.2 to 1, which is the optimal range for complete combustion, maximum thermal efficiency, and minimum heat generation. The factory lean calibration on many Euro 5 machines runs between 13.8 to 1 and 14.7 to 1 at partial throttle in the lower gear range. That difference is not abstract. It is measurable in the exhaust gas temperature, felt in the heat coming through the engine cases, and experienced as the disappearance of lean surge after a proper tune. The smoothness improvement from correcting the air-to-fuel ratio is immediate and dramatic. The snatch from rest disappears. The lean surge at motorway, constant throttle disappears. The gear changes become smoother because the engine is no longer oscillating between lean and slightly less lean during the shift event. First, second, and third gear transform from dead, restricted, frustrating zones into honest representations of the engine's actual capability. Operating temperatures drop by between 15 and 30 degrees Celsius at the cylinder head under sustained partial throttle conditions. This is not a marginal improvement in any sense. Running 30 degrees cooler under sustained load extends valve seat wear intervals, reduces thermal stress on piston rings, decreases the rate of engine oil degradation, and lowers the probability of heat-related electronic component failure. A proper tune does not just improve the ride, it extends the life of the machine. The power delivery becomes linear, not dramatically more powerful, though peak power typically increases by between 5 and 12 horsepower on a previously restricted machine. The critical improvement is not peak power, it is predictability. A linear throttle response, one where the engine delivers exactly what the rider's hand requests throughout the entire gear range, is a safety improvement. A rider who can accurately predict the response they will receive from a throttle input makes better decisions in traffic, in corners, and in emergency avoidance situations. The tune is not an upgrade. It is a completion of what the manufacturer was forced to leave unfinished. And now, with all of that knowledge assembled, it is time for the decision every buyer of a modern motorcycle must make. Chapter 7. The verdict. You are standing at a fork in the road. On one side is every new motorcycle sold in 2026, running Euro 5 or Euro 6 calibrations, producing compromised throttle response, excessive heat, lean surge on the motorway, and dead zones in the lower gear range that make urban riding feel like arguing with a bureaucrat. On the other side is every one of those same machines after a professional ECU flash, running at the temperatures and response characteristics the engineers designed, and costing an additional $800 to $1,500 that the brochure never mentioned. For buyers of brand new machines still under warranty, the smart approach involves a clear three-stage decision. Stage 1 is to live with the factory calibration for the full duration of the warranty period. Document every heat-related issue, every lean surge event, and every stalling incident in writing to the dealership. Create a service record that establishes the baseline behavior of the machine before any modification. Stage 2 is to flash the ECU the week the warranty expires. Stage 3 is to never buy a new motorcycle from a manufacturer who ships a machine that requires a third-party correction to perform as advertised. For buyers of used Euro 5 machines already outside their warranty window, the calculation is simpler and more direct. The hidden tuning tax is a mandatory line item in the purchase budget. Factor $1,000 minimum into every used Euro 5 purchase budget. If the machine has already been flashed by the previous owner, verify it with the tuner's full documentation, confirm the specific map version installed, and have the air-to-fuel ratio validated on a dyno before riding the machine hard. A badly executed flash creates problems more severe than the factory calibration it replaced. For riders considering pre-Euro 5 machines, specifically anything manufactured before the 2021 implementation date, the analysis produces a different conclusion. A properly maintained pre-Euro 5 motorcycle delivers mechanical throttle honesty, lower operating temperatures, and a riding experience that modern electronically throttled machines have failed to replicate despite 30 years of supposed advancement. The used market for these machines is undervalued relative to their actual riding quality. The depreciation curve flattened years ago. They represent exceptional value for the buyer who understands what they are choosing. The manufacturers are not the villains in this story. They are building machines to the specifications regulators demand, in markets they cannot afford to exit. The engineers know what the factory map contains. The homologation teams know what was sacrificed. The dealerships know that the aftermarket tuning industry exists for a reason. The villain, if there is one, is a regulatory framework that imposes emissions standards through calibration restrictions rather than through genuine engine technology advancement. Standards that punish ride quality to achieve test results that do not reflect real-world emissions performance. A framework that passes the cost and the inconvenience directly to the rider, while the brochure claims 120 horsepower with a straight face. Every rider who buys a modern motorcycle in 2026 deserves to understand exactly what they are buying. Not the specification, not the headline number. The actual machine, the actual map, the actual gap between what was promised and what was shipped. That gap is real, and it is documented. It is measured in horsepower locked behind firmware, in heat generated by a lean calibration, in dead zones placed exactly where the regulations required them, in $1,000 minimum that no dealership will ever tell you that you need to spend. And until manufacturers are required to disclose the factory calibration restrictions on every specification sheet, the responsibility for that knowledge falls on every rider who values understanding what they paid for. Click the next video on your screen right now to discover which pre-Euro 5 machines deliver everything modern motorcycles are withholding from you. Stay sharp, stay tuned, and I will catch you over there.